Magnesium is integral for 600 plus biochemical processes in the human body, and yet most people are deficient. Common signs of magnesium deficiency include fatigue, muscle weakness, stunted growth, poor immune function, poor concentration and memory, hormonal imbalances, bone and teeth problems. Most people think grabbing a bottle of whatever cheap stuff on the shelf or at the top of Amazon will solve this. The common misconception is that consuming more magnesium will automatically improve health and well-being. The truth is, there are various forms of magnesium, each of which is essential for a variety of physiological processes. Most people are deficient in all forms of magnesium, while even those considered healthy typically only ingest one or two kinds. Consuming all 7 of magnesium's primary forms is the key to accessing all of its health benefits. That's why we pack 7 forms of 450 milligrams of elemental magnesium into each serving of Wild Mag Complex. 1 dose a day is all you need. Learn more and grab a bottle today at wildfoods.co. Use code GENIUS for 10% off your order.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Dr. Gabriela Kalčíková. She's an assistant professor, university in Slovenia. It's called Ljubljana. I probably mispronounced that, but she'll pronounce it better. And we're going to talk about microplastics and her research. So, Gabriela, thank you for coming.
Hello, Richard. Thank you for having me.
How do you pronounce the university's name properly? Sorry.
It's the University of Ljubljana.
Ljubljana. Okay. All right.
Yeah, no problem.
Well, tell me a bit about your background and how you got interested in microplastics.
Mm-hmm. So I'm a chemist, and I studied chemistry and environmental technology. And then I did my PhD on waste management, which doesn't sound really exciting, but it was a nice project. And in one part of the project, I had to set up a landfill. So I had to put waste into a pilot landfill. And when I was putting all the waste there were actually a lot of plastics flying around. So then I start thinking, like, what will happen in the environment when they escape the landfill or wherever they are. And actually, when I completed my PhD, then I decided to focus on plastics and microplastics. Actually, it was obvious choice for future research. So it's actually, I would say, my research on waste management.
What happened with the landfill? You modeled a landfill, and did you look at leachate, or what was that project about?
It was. It was about actually the first idea was to find a way how to treat landfill leachates. And I was trying different methods and combinations and how to make it, and different new approaches and enzymatic treatment. And then I actually realized that it's almost impossible. The leachate is so polluted that it's really difficult to treat it. So then I was thinking, like, to switch into what about to change the waste management. So how to do it differently, how to landfill better, or somehow that the leachate will not be so polluted. So because there was really a big change of waste composition over last years, because we started with sorting of waste. So the composition of the waste is not the same like 20 years ago. So this was the idea to see what will happen with the leachate when you will use only residual waste. So then it was the landfill was about like 1 cubic meter big, and then I put the waste there, the residual waste, but still in the residual waste there was a lot of plastics because you just cannot recycle everything. So then actually it was interesting with the residual waste, when you don't have any organic waste, if everything is properly separated, the leachate was not very toxic. it was actually much better than the traditional way when you mixed all the waste together and put it to the landfill. But anyway, landfilling in general is not an option. But it was interesting to see that when you change the composition of waste, then also the leachate, it's not so dangerous than before.
Quick question too. What were some of the most dangerous components to have in landfill that caused extremely toxic leachate?
I think if this is actually the problem of inappropriate waste composition. So, for example, I think 20, 30 years ago, there was actually not a lot of knowledge what we can landfill. So they were putting basically everything, also batteries. So there were heavy metals, or there were also a combination of industrial waste, because they were just putting municipal waste and industrial waste together. So there could be a lot of dangerous components. But this changed a lot with law, with changes in law, and also with the education that people, they know what to put to the bin for waste. So I think now you cannot find so many dangerous components in waste in general. But to think about sustainable living, landfilling is really the last option, because then it's the material is lost, and anyway, landfilling, it's a way how to bring the waste under anaerobic conditions. So it means that the methane is produced, and if you don't capture all the methane, then it's going to the atmosphere and it's making problem as CO2. So I think I think it was good to see that with proper waste separation you can do a lot, but anyway, it's not the way how we would like to treat the waste in the future.
All right. And then moving on to microplastics, you noticed that there was microplastics swirling around. So how did you end up researching them, and what's your research about?
Mm-hmm. So actually I was, the beginning I heard about microplastics in cosmetics, and I was kind of shocked, because then when I wrote the first paper, then I returned back home, and then I checked my cosmetic products, and then I was really shocked that there's microplastics almost everywhere. So I started just to see what is inside, and with the characterization. So first I dissolved the products and to got the idea how much of microplastics is there, and what is the composition and the particle sizes. And then I wanted to know more about if it is important source of microplastics for the environment. So I was working on wastewater treatment. So how many microplastics can be accumulated in wastewater treatment plant, and then how many of them can actually enter the environment. And this was also very interesting to see that for cosmetic products, there was really a lot of microplastics coming through the wastewater treatment plant.
Well, in wastewater treatment, when they go through flocculation, do they put anything in there to take microplastics out of the stream, or do waste treatment plants not even recognize that microplastics are in there?
Because it depends again on the law for each country. So in some countries you have requirements for a high quality effluent, so they have more treatment steps, and microplastics can be removed. So it depends on the treatment technology. If you have the conventional biological treatment, so first you need to have some screens to remove bigger particles in general, like small pieces of wood or stones or whatever. And then there is a primary settling tank, and then you have the biological treatment. So you can remove basically from 80% of microplastics by the conventional system. The problem is that so many of microplastics are coming into wastewaters from synthetic textile like fibers, or from the cosmetic products.
Magnesium is integral for 600 plus biochemical processes in the human body, and yet most people are deficient. Common signs of magnesium deficiency include fatigue, muscle weakness, stunted growth, poor immune function, poor concentration and memory, hormonal imbalances, bone and teeth problems. Most people think grabbing a bottle of whatever cheap stuff on the shelf or at the top of Amazon will solve this. The common misconception is that consuming more magnesium will automatically improve health and well-being. The truth is, there are various forms of magnesium, each of which is essential for a variety of physiological processes. Most people are deficient in all forms of magnesium, while even those considered healthy typically only ingest 1 or 2 kinds. Consuming all 7 of magnesium's primary forms is the key to accessing all of its health benefits. That's why we pack 7 forms of 450 milligrams of elemental magnesium into each serving of Wild Mag Complex. 1 dose a day is all you need. Learn more and grab a bottle today at wildfoods.co. Use code GENIUS for 10% off your order.
So, and we are also treating a lot of wastewater. So anyway, even if 80% of microplastics is removed in the conventional system, then a lot of them is actually carried into the environment. If you have a special advanced treatment, for example, membrane processes, or if there is also like coagulation and flocculation, then you can really remove almost everything from the wastewater.
Are there any countries that are processing wastewater treatment effluent to a very high level? Like, do you know if the U.S. is doing it or anyone that's piloting this?
I think there is not really now law for microplastics, for example, that you would have effluent limit for wastewaters. For example, how many microplastics it can contain, because still the monitoring, it's really demanding, it's really difficult. And I would say that most of the time we do it during our research work, that researchers are interested in efficiency of wastewater treatment plants, or they are focused on the stages where it is removed and what is the fate of microplastics in a wastewater treatment plant. But I think there is not like requirements for wastewater treatment plant regarding microplastics. It depends on the country what are their requirements for the effluent in general, and usually they are focused on organic compounds, they are focused on nutrients. So if they have some special additional treatment, for example, the last step is membrane process, like ultrafiltration, then they can also remove microplastics. But in general, for example, here in Slovenia, it's the primary treatment and the secondary treatment with biological activated sludge. And then now there is for several years new law to remove nutrients. But they are not law against microplastics, or that we would have a law to treat the effluents that they would not contain microplastics, or that there would be just a certain number of particles.
So what are the effluents of wastewater treatment plants look like? What kind of microplastics end up in the water? Is it a lot of fibers? I mean, where do they come from and what are they?
Yeah, so there's a lot of fibers, because always when you do laundry and you have synthetic clothes, there is a lot of fibers generated. And then from cosmetic products, but now I think it's less, because in many countries the ban against on microbeads in cosmetic products was very efficient. And also a lot of companies decided not to put them into their products, because there was a big pressure from different groups. NGOs, they were really against, and this really helped a lot. So actually cosmetic companies, they decided not to put them there, because they realized that consumers, they will not buy the products, because they were really aware of the problem. But in general, fibers, and then whatever people just put to the toilet and should not be there, and it's from plastics. Because when like plastic bags or items are going through the sewage system, then they can be disintegrated into smaller particles. So these are microplastics that can then appear in the wastewater treatment plant, and also those they can go through some of them and to be in the effluent.
So what is your research focused on?
Actually, I'm working on strategy, phytoremediation strategy to remove microplastics from water. Because in one of my earlier research, I was investigating interaction of microplastics with aquatic plants. It was in year 2017, because until 2017 there was some research on microplastics and interaction with animals. Usually researchers, they focus on ingestion of microplastics and what will happen in the organism, in the gut. But that time I worked also with the floating plant, duckweed. It's very widespread. You can see it basically everywhere floating. And then I was thinking, when microplastics are floating, so what will happen when they will meet the floating plant. And it was very interesting. There was some effect on the roots, but more interesting was that the microplastics, they actually attach to the surface of the plant. And then I got the idea that maybe if the microplastics can attach to the plant, that we could collect them by the plant. So these methods are called phytoremediations. So we are using plants for cleaning the environment. And I have been working on this topic for last 6 years, let's say. Last 3 years more intensively with my PhD student, and now we got really interesting results that we can collect by the plant, like with one planting about 20-25% of microplastics. So we are now more in the modeling how this could be efficient for natural environments. It's really exciting because I'm an environmental engineer, so I was always like trying to find a solution. When I was working, doesn't matter if I'm working with landfill or if I'm working with microplastics, I was always like, it's great to understand the processes and to have the description, but even better, it's to find a solution for the problem.
You're studying plants that attract microplastics. Do they get integrated into the body of the plant when it's consumed? Or you're looking at the the water that maybe is used in a hydroponic system? Like what's the context in which you're looking at plants and microplastics?
So microplastics that we sample in the environment, in general, they are too big to be incorporated into the plant. So the plant uptake proceeds just for very small particles, for let's say nanoparticles. So we are working more on absorption of microplastics on the plant. So the idea is that you have, for example, a lake where you have microplastics, and then you add the floating plant, and during the growing season it will grow. It will collect the microplastics, and also it's great to have plants there because they can help with removal of nitrogen and phosphorus. So it is a win-win situation because it is also cleaning the water from nutrients.
Would this be like a floating raft of plants?
No, they're very small floating plants that are floating naturally. So they're called.
Yeah, because I was picturing a floating raft, but then I saw the styrofoam in my mind, and I was like, no, that's not good either. Yeah.
No. This is just the plant. It is a floating plant. It floats naturally. It's widespread. It's basically everywhere, and it can just naturally be in the environment, in lakes or ponds. So the idea is to put the plant there. It will float and grow and pulling the mixroplastics, and then several times during the growing season you can just collect it. So it's kind of like cleaning system to remove microplastics. But of course, then we have to be aware of plant with microplastics. We have to do also with something with this. So there is one option to do incineration, or there is also option to reduce the amount of biomass with the microplastics by anaerobic digestion, for example. So, but we have to keep it in mind. It's not that the plant would destroy the microplastics. It is just an efficient way how to collect it from water surface.
So what would you envision? Seeding a lake with these tiny floating plants and have them clear out, some of the microplastics, and then harvest the plants and concentrate them and burn them? Or what would this look like?
Yeah, it would be like this. We have to then take care of the biomass. But this is using plant for removal of pollutants from natural environment, from water. Like this, it's quite common. But usually it was used for removal of metals, for example, because they can absorb the metal. So, but then always you have to collect the biomass and you have to get rid of the biomass. So it is way how to remove pollutants, different pollutants from the aquatic environment, that you don't have to, because it's impossible, for example, for lake to treat the water. So you need to do it there, so at the place. And this is the way how it can be done.
So what kind of plants are these that float, and do you have a setup, at a local river where you're trying this, or lake? Like where is this being demonstrated?
We started in a laboratory, so we have mainly now laboratory results, and we are now working on the mathematical description of the process to understand it better. And actually the next step is to do a pilot pond and try it under natural conditions, because it can be a bit different than in the laboratory. For example, you have also naturally rain. So what will happen when this tiny plant with attached microplastic will be under a heavy rain? So it's the question if the microplastics will stay attached, or how it will be when there will be wind or more moving. We try to simulate some moving on the orbital shaker and so on, but it's still not the same when you expose it to the natural conditions. So under laboratory, it works well. Now let's see. This will be the next step.
What does the lab setup look like?
Okay.
Is it a flow system, or what does it look like?
So we were working with two systems. First, we did the experiments in a beaker. So it is like very small environment, I would say. Then the next setup that we tried, it was in a constructed wetland. So when we have a laboratory constructed wetland, which is like, I think, 1.5 meters long and 0.5 meter wide. And then we have the floating plant there, and then we release the microplastics, and then we were evaluating how many of them will be catched by the plant.
All right, so what are you noticing? Do the plants preferentially pick up certain kinds of microplastics and not others?
We worked on different microplastics and also natural particles. We tried with polyethylene, with fibers, polyethylene terephthalate, and also with rubber tires. And we could see that this method would be the best for polyethylene, because both they're floating, the plant and also the polyethylene, when it is released from wastewater or from different sources initially, it floats on the surface, so the plant can easily catch it, compared to other types of microplastics that have a higher density. Then they are for some time the water surface, so they can be in contact with the plant, but then with time they are actually getting, like, because of the water movement, they are getting into the water body, and then when they are there, the plant cannot catch them anymore. So we were quite successful with polyethylene. Compared to natural particles, the natural particles, they don't attach to the plant, which is probably because of they have the same charge, because they are both plants. And also the natural particles, for example, from cellulose, they are both a minus charge, so they don't attract to each other. So we have very good results with polyethylene, which is good because there is a lot of polyethylene coming into the environment. Polyethylene floats initially. So I would say that this would be a very good system for catching the fresh microplastic pollution which is coming from different sources. And because with time, we know that microplastics, especially those that are floating, they are exposed also to sunlight, and there is also, with the water movement, there can be a lot of microorganisms then attached on the particle and creating biofilm with algae. And then with increased density of the particle, the particle will actually disappear in the water body, and then it is also lost and the plant cannot catch it anymore. So the main idea is to try to collect the fresh pollution microplastics that are just coming to the natural water, and that we would collect them by the plant, or the plant would stabilize them at the water surface, and then we can collect them.
What happens to the plants, though? Are they ground up with the microplastics, or how are they processed?
Mm-hmm.
Reused, maybe cleaned and reused, or is the plant incorporating some of the microplastics into itself so it's integrated into the plant?
It is attached to the leaves and to roots. So it is not incorporated, but we tried also different procedure how to evaluate the strength of the interactions. And they can be also very strongly attached to the plant. So it stayed with the plant. But we were running also really long-term experiments, like for 12 weeks, and there was not any effect on the plant. Initially, it is affecting roots, but after 8 weeks, the plant adapts. So in general, the plant that we selected, the floating duckweed, it is very good model plant because it is not affected by microplastics, and the attachment for polyethylene or the interaction with polyethylene is very good. So this was, I would say, a very good combination, because you always have to be careful with the phytoremediation methods that the pollutant is not killing your plant or your organism that you want to use. So with polyethylene and with microplastics in general, we were lucky that the plant can survive and can adapt also to the presence of microplastics, and therefore it could be really useful for the collection of microplastics.
But biologically, what's the sweet size? You said earlier in the podcast, a lot of the microplastics you've seen are too big, maybe to have biological effects. But what is the sweet spot? Is it like 1 micron or less? I know like inhaled particulates, I believe 1 micron size is a bad size because they tend to get lodged in lung tissue. But what about biological systems and microplastics? What's been observed?
We are working with microplastics that are I always call it environmentally relevant microplastics, because I always search for microplastics, for research on microplastics, for monitoring. So we always prepare our microplastics that we are using for experiments that are environmentally relevant. So it means that they have the size, the shape, and the material that has been found in the environment. So all our experiments were with microplastics that are about 10 micrometers in average size, about 100 micrometers, because they are the most abundant in the environment. And these are like attached, and maybe I would say that we are working with sizes up to 1 millimeter, because it's also something that is, I would say, the most abundant fraction. But when you have smaller particles in nanometers, then they can really get into the organism and then affect it. But like this, with the plant that we were testing, it was okay.
All right. So, I mean, I know that there's even down to nanoplastic size, but you don't see that that's a large fraction of microplastics in a given like aquatic system. They tend to be around, when you say like 100 microns and up.
Mm-hmm. Because it's very difficult with nanoparticles, nanoplastics, to monitor them in the environment. I think there are not even methods now for it, because it's even very difficult to get information about very small microplastics, about 1 micrometers. You imagine that you have a net, and then you want to collect microplastics, but you are collecting everything, algae, whatever is in the in the water body. So it's then really difficult to recover microplastic of bigger sizes. So these very small sizes and nanoplastics, it's almost impossible to get information about how many of them are in the environment. And I think we will need better development of analytical methods for identification of nanoparticles, nanoplastics in a natural environment, because so far methods that are used for characterization of microplastics, they can get down to 1 micrometer, but not lower. So even if you sample something and then you think it's a nanoplastic, and you see it, for example, under electron microscope, so you can see nanoparticles, you don't know if they're plastics or if they're some other nanoparticles. So it is really difficult, and I would say most of the research now on the nanoparticles is by using industrially produced nanospheres, because those are easily to obtain to buy them. But if you want to have like nano fragments, it's much more difficult to get them for your research.
Well, what is the size limit that you've seen analytical techniques can observe microplastics? What's the smallest size that's reasonable right now?
Well, I think it depends on the analytical method, but for example, the typical analytical methods that are used for identification of microplastics are FTIR or Raman. So those, I think they can go to 1 micrometer. So you can be sure that the particle that you can see is actually plastic particle, because you are getting the information from the analytical methods, you're getting the information about the chemical composition. So if you sample them in the environment, I think you are sure about particles 1 micrometers and larger. For smaller, I think it's very difficult, and maybe some special research is going on now on how to get to smaller sizes, but it is not something that would be common in microplastic research.
Okay, well, very good. What's the best place for people to find out more about your work? Where can they go?
So I have a web page which is called Planterastics. It is from my initial work, interaction of plants and microplastics. And we have also Facebook and Instagram with the same name. And we are quite active because I think it's really important to share the knowledge about microplastic research and plastic waste management in general. Because microplastics and plastic waste that we really don't want to see in the environment, it's actually a result of our actions, because plastics, they don't naturally exist in the environment. We are responsible for microplastics and plastics in the environment. So it's really important that people understand the problem. And this was actually very nice to see when I mentioned about microbeads and how people refuse to buy products with microbeads, with microplastics. I think this was a very good example how awareness can really change a lot. So we have very active Facebook, Instagram, and webpage. So it will be great if people would check and interact with us. And if there are questions about microplastic research, I will be always happy to answer them.
Very good, Gabriela. Thank you so much for coming on the podcast. I know it's late night for you, but again, thank you.
No problem. Thank you very much for the invitation.
Magnesium is integral for 600 plus biochemical processes in the human body, and yet most people are deficient. Common signs of magnesium deficiency include fatigue, muscle weakness, stunted growth, poor immune function, poor concentration and memory, hormonal imbalances, bone and teeth problems. Most people think grabbing a bottle of whatever cheap stuff on the shelf or at the top of Amazon will solve this. The common misconception is that consuming more magnesium will automatically improve health and well-being. The truth is there are various forms of magnesium, each of which is essential for a variety of physiological processes. Most people are deficient in all forms of magnesium, while even those considered healthy typically only ingest 1 or 2 kinds. Consuming all 7 of magnesium's primary forms is the key to accessing all of its health benefits. That's why we pack 7 forms of 450 milligrams of elemental magnesium into each serving of Wild Mag Complex. 1 dose a day is all you need. Learn more and grab a bottle today at wildfoods.co. Use code GENIUS for 10% off your order.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.